Well, it's almost lunchtime, so let's do this. Opening question. How many of you think that all of the C and C++ on GitHub has 100% memory safe and thread safe guarantees? Show of hands. One person. All right, we should talk later. Related question. Who on your team would you trust to write 100% memory and thread safe C? Yourself? One person, same person. What about a new junior on your team who's never written any C or C++ before? No people on that one. What about GitHub Copilot? Okay. This is, she said I like Rust, I do. Same question, thread safe and memory safe, safe code written in Rust on your team. I'll trust everybody on that list because the compiler's got my back. This is not a talk about C and Rust. We can talk about that some other time. This is a talk about our engineering systems and how they interact with large language models. Because large language models are now and are increasingly pervasive. And my thesis is that our engineering systems are not ready for a world where large language models are pervasive. Now, if you're in the room and you're a big fan of LLMs, cool. This talk is about how do we get better results out of LLMs in our engineering systems. If you're in the room and you're, like me, a little more skeptical, maybe very skeptical of the hype levels out there right now, this talk is about how we can put good safeguards in place to make it so that LLMs don't burn down the world of software quality. It's bad enough as it is. Over the last few years, the phrase prompt engineering has been bubbling. You haven't been able to go anywhere without hearing it. This sort of emerging discipline of a new kind of engineering. How do you get the best results out of a generative AI system? Things like specific choices in wording or the amount of context you include, the scope of the task that you give it, smaller tasks, more achievable. Creativity levels, what's the temperature in your system? What are the tasks where you just looking to say, it's going to get this wrong every time, don't bother. And one of my favorites, meta prompts, like no blabbing. If you haven't tried that one, try it. It makes them a bit less chatty. And this is good. This is a skill that if you're using it, you do get value from developing. But there is a problem. And that problem is the opening slide I showed you. All of our LLMs have been trained on real-world code. They've been trained on the corpus on GitHub, for example. And no matter how good your prompting skills are, there is a ceiling on how memory safe C, or unsafe Rust, for that matter, can be. And the ceiling is C. It's not the LLM itself, and it's not the prompt you give it. And there are things we can do that help with that somewhat, but only somewhat. No amount of prompting, well, okay, look, telling Copilot no memory vulnerabilities, please, probably will get you better results. So if you're writing C with Copilot, do that. But it doesn't actually solve the problem. In these kinds of things, memory safety, or lots of other problems, as we'll see, prompt engineering is not enough. And more than that, I assert prompt engineering will never be enough. That's a strong claim, so let's dig in a little. A substrate is a layer that sits below the thing we're notionally interested in. In biology, for example, the substrate is the environment. If we're looking at a ladybug, it might be this leaf or the forest it's living in. It's the material it grows on, maybe what it eats, where it lives. And that substrate informs everything about the creature's existence. Even though maybe you're studying what does the ladybug do, you can't actually understand that, and it can't actually live without the substrate. Bring it a little closer to most of our field of study with something like chip manufacturing. A substrate is the silicon wafer. Now, the silicon wafer doesn't do anything itself. It's inert. The chip is the active part. But if you don't have a good wafer, you don't have a useful chip. The substrate shapes the active agent that you care about, even though most of the time you end up thinking about the agent. And when we bring that around to large language models, Well, the substrates are the training data that you end up with the model itself, any reinforcement learning that it's gone through, any kinds of feedback systems that it's gone through, and then the output, the engineering systems where we run the model, whether that's deploying an agent or whether that's using Copilot to generate some code. And just like with the chip manufacturing and just like with biology, these factors will dominate any amount of prompt engineering you do. You can't get better results than the model has inputs. And you can't get better results than your engineering system is prepared to support. There's another problem. At the intersection of automation and attention, we have a few decades now of research on what happens when you put autopilot systems in place, whether that's for aircraft or whether more recently for self-driving cars. It turns out that human beings, namely us, can't pay attention only when we need to. If you say, it's fine to not pay attention now because your car will drive itself, which, spoilers, it's not going to drive itself. But if you say that that is true, people will disengage. And we see over time that for pilots, for example, accidents happen because even though they have a high degree of trained competence, when they have relied on the autopilot, one, the trained competence degrades if they're not actively doing things to maintain that competence over time. And two, even when they have, when the situation goes from the autopilot is fine to the autopilot is driving you into the ground, if you're not able to attend quickly, you go into the ground. We can summarize this with a rule of thumb. The better that an automation works, the less we attend to the thing being automated. I'm going to say that again. The better that an automation works, the less we will naturally tend to attend to the thing being automated. And it turns out there's no reason to think that that applies to aircraft and automobiles, but not to GitHub Copilot. Now, you might be thinking, well, but are the consequences as severe as all that? And the answer is, have you been paying attention to the conference for the last day? Sometimes they are, and not just when rockets are involved. More subtly, though, those consequences can be very serious and happen at a significant time remove from when you accept the prompt, which means it can be hard to see how that choice to accept the result from a prompt translated into a serious system failure later, unless you're logging every single piece of code that got generated by an LLM. And we can combine that with another, let's call it a challenge, which is that code review is hard. If you're reading someone else's code, or, I open pull requests and review my own code just to try to get in a different frame of mind, spotting bugs in code, whether at the architectural level or the small implementation detail level, it's hard. We know that experientially from debugging, right? When you're debugging something, you know there's a bug there. And it's still hard to spot it in a program's text or in the interaction between different programs. But when you prompt Copilot and say, hey, give me some code, please, and then you're checking its results, you're doing code review now. You're looking for bugs. You're looking for bugs in the immediate code, and you're looking for bugs in how it relates to the system around it. And that's hard. When we put these factors around things like code review and automation and attention together, we end up with what was, for me, a somewhat unintuitive result, which is that the better that large language models get, the more they boost velocity by generating actually working code, the harder it will be for us to spot it when they get it wrong. So what do we do? I don't think LLMs are going anywhere, but if we're going to deploy them, I think, number one, our software foundations just have to get a lot better across the board. Resiliency, robustness, et cetera. And we're going to work through a worked example of that in a minute. But I want to talk about it in the sense of defense in depth. It's not one technique. I like Rust, but Rust isn't going to save you from this by itself. It might help, but you're not going to get there without testing and lots of other things. It also, though, means making firm judgment calls about where large language models do and don't get deployed. Thinking again about safety, about security, about some of the things we've heard about in the last day. Again, the obvious one of, do you deploy it in a medical system? No! But also things like, okay, maybe it's fine to use an agent-based system to build some refactors and accelerate something or get something refactored that was never going to get refactored if you didn't do it with something like this. Should it be offering legal advice to people? Should it be making legal decisions about people's lives? Absolutely not. So we need to be doing both of these as engineers and as people who claim that title for ourselves. There's one more problem we need to talk about before we dig into a short worked example here. It's the elephant in the room, hallucination. Hallucination is not a solvable problem with the architecture of LLMs because hallucination is really the wrong word to use for this, and it makes me very sad that it has caught on because it suggests that sometimes LLMs don't hallucinate, which is backwards. Hallucination is what LLMs are. They're predictors over tokens. And you know what? That's fine. Like, we've built some really cool things with them. They're really interesting. One of the reasons I don't think they're going anywhere is that fact. But when ChatGPT gives you the right answer, it's doing the same thing as when it gave you the wrong answer. If we understand that, then we can, and the thesis of this talk is we must, build our software and our systems to account for that. Build our socio-technical systems to take into account what LLMs are. Substrate engineering. So let's do some. If we're going to do this, we need to operate under 3 key constraints. The substrate and the environment is going to fundamentally shape, inescapably shape, the results we get if we're allowing LLMs to be used in our systems. Automation and attention relate the way they relate in humans. So our systems have to take that into account. And last but not least, LLMs work the way they work. If we don't fool ourselves about that, we can build good things. So, what is substrate engineering? Well, it's everything. It's all of our engineering foundations, right? Tooling and configuration, programming languages, API design. Let's think about correctness by construction. It's what do we say about testing when LLMs are generating a bunch of our tests now? How do agentic systems work? Where are they appropriate to deploy? How do you engineer around them? Should our package managers be allowed to run arbitrary code every time they install things? No. Can we get operating systems that embrace capabilities models and actually sandbox things better? Yes. We don't have time to talk about all of that, especially before lunch, so I'm going to talk a little bit about tooling and configuration and kind of give us a worked example of how do we do this kind of substrate engineering. And I'm picking tooling and configuration, first of all, because I think it's underinvested in. We've treated it as a second-class area for a long time. But also because it has a disproportionate impact on both user and developer experience. Tooling and configuration languages and things like that tend to sit at really critical points in our software systems, how developers work and how users actually end up interacting with our systems, though not directly. And that's true regardless of LLMs. But things get more interesting when we put LLMs in the mix because, one, these kinds of tools and configuration languages, for example, are very amenable to use with an LLM-based system because they tend to be, pretty regular. But they're also vulnerable to the kinds of problems that LLMs have, right? There's a lot of Circle CI configs or GitHub Actions configs on GitHub in that corpus. So there's a good chance that if I prompt Claude and say, hey, write me a GitHub Actions config, it'll probably give me something useful. But as we saw, hallucination, fundamental. I can only ever say probably. And when we extend that out, okay, that means that LLMs are places where these kinds of tools are going to get used a lot in practice, but it also means that they're places where the risks can be quite high. How many people here have experienced an outage due to a bad configuration value in a YAML file? That's almost the whole room. Both of the worst outages I experienced in my time at LinkedIn, that's why. So let's walk through this a little bit. Here's a broken GitHub Actions config. It's written in YAML. has a job named test, and it runs on Ubuntu latest, and it has 2 steps. It checks out the code, and it runs the test, make test. And it does that on push or release. There's probably 3 GitHub Actions wizards in the room who are like, I see how this is wrong. But I didn't. I can't see just looking at this. I mean, I can now because I wrote this slide. But 2 weeks ago, not a chance. If, however, my editor says, hang on, bright red squiggles under the entire job definition, and then provides the not so helpful but better than nothing error message, job section is sequence node, but mapping node is expected. OK, I can translate that to this is supposed to be a key value pair. Test is supposed to define an object that now has these steps. And it can still have name in it, but it has to be this. OK, cool. We know how to do better with programming languages than JSON schema-based validation for YAML configs. We've got decades of research into programming language usability and design. And a lot of us, dare I say, don't have JSON schema validation wired up for our YAML configs to make sure that they get through, get checked in CI. If you're not doing that, please do that. But we can do better than this. So I'm going to suggest, as a worked example here, what would it look like if we think about substrate engineering configuration languages, infrastructure as code, things like this. And gladly, people have already started doing this. For example, Pulumi lets you use TypeScript or Python or .NET or Java or Go or write your own bindings to their SDK. And now you can check it in as code, and you can get a lot of benefits from that. Cool. I mean, for that matter, F# has had its fake DSL. It's like Make, but in F#, and frankly, a lot nicer than Make. Thing I learned during this talk, Make is a Turing-complete language. This is great. We get all the benefits, all the power, all the tooling that come with full programming languages. There's a problem with using full programming languages here for these kinds of tools, which is they can do anything. For example, they can get into infinite loops while you're installing your dependencies. They can throw undefined is not a function while you're trying to deploy. Thanks, JavaScript. They can throw a null pointer exception when you're trying to run CI. Thanks, Java. And that's regardless of whether we have LLMs in the mix. But if we're trying to write this kind of code with LLMs, and again, I hypothesize that this kind of code is especially likely to get written with LLMs, then those kinds of problems are things we need to think about. So could we make a language design that solves some of those problems? Not all of them, but some of them. Sure, yes, we could, actually. There are useful properties we could have in a configuration language that would help with this. These properties are rare in most mainstream programming languages, but hey, soundness. Not having undefined is not a function or null pointer exceptions, that would help. It'd be a meaningful improvement in what kinds of things can go wrong when we're trying to run CI, which theoretically is about checking that the rest of our system isn't broken. I would like this part of my system not to be broken. Another property that's nice to have if you're running a build system is knowing that it'll stop eventually. Now, termination is hard. Some of you are thinking, but the halting problem. Yes, but the halting problem is only something you have to care about if you have a Turing-complete language. We don't have to have a Turing-complete language for this. This is why we use YAML, except you can encode Turing-complete languages in YAML. But if we restrict what the program can do, we can solve this. We can have totality, which just means that every input to a function gets an output. Yes, that means your programming language now needs to understand that n divided by 0 could be a problem. This is easier if we have pure functions, so that the same input always gives you the same output. Also, that sounds nice for build tools. And then we just need to get rid of anything that is or can be compiled to a while true loop, general recursion. If we do that, we get totality. It would also be nice to have a nice type system so that we can say type track is individual contributor or manager without needing to jump through final subclass shenanigans and what. Like, no, let me express this kind of thing in the programming language. And also give me type inference so that I don't need to be like, wait, what is the type here? And I don't need to write tons of boilerplate. One of the reasons we go for languages like Python for configuration languages is because it's nice. You just kind of want to knock it together and go. And boilerplate gets in your way. So this sounds nice. That last one is suggestive. Make your type system nice, but not too fancy. Like, we don't need Haskell or Rust level type systems for this. We want something a lot simpler. Elm, F#, Swift, something in that space. Maybe not Swift even. If we did that, we'd get some wins out of it. You'd get faster feedback loops for the people writing the configuration, with or without the LLMs, because you've got a type checker saying, whoop, that's the wrong thing, and you have the ability to express invariance in your code, not just with JSON schema. Cool. Ugh. And most of the time, when we're working in our engineering systems, like if you work at OpenAI or Anthropic, this isn't true, but most of us don't have a particularly strong way to influence the input side of the systems. But if we had a lot of config written in languages like this, we actually do start to get to influence the input side to the system as well. So training data would be more correct. And this gives us a higher chance of getting things right from the start. Now, this isn't a silver bullet. There are no silver bullets in software. But having the right tools in our toolbox, having better tools in our toolbox helps. And again, defense in depth. We don't have to solve all of the problems with any one tool to make things better by applying lots of good tools. Is there anything out there that does this? Well, Starlark, the Bazel and Buck build tool language, does take some steps in the right direction. Some. Soundness is not a thing because it doesn't have a type system. I'm aware Meta has an experimental thing you can use, but basically it doesn't have a type system, so it's not going to help you on that. It does a little on termination. You can't do general recursion in it. You can still do n divided by 0, so you don't have totality or any of that. And again, no rich type system, because no type system, woo! Another option in this space, which most of you probably haven't heard of, is DAL, and it checks the boxes pretty well here. It's sound, has a nice type system. It does guarantee totality, which is handy. You can't solve things like for I equals 1 trillion, but other than that, you get there. It has a nice type system, nice errors. But again, lots of people use Bazel and Buck. If you're not using anything like that, it might be worth looking in. No one's heard of DAL. But now you have, so you might check it out. And if you're a little adventurous, you might try it, because it compiles to JSON and YAML, which means you can have all of those nice experiences and gradually adopt and migrate to it. I think we could also invest in building stuff in this space. Get some of those, it's kind of like Python that Starlark has, but these, it's robust and resilient that DAL has. But does it work well in practice? I don't know, this is a hypothesis. We should try it. What are the trade-offs? Does it actually help with LLM-generated code? I think so, but we haven't built it yet, so let's go do that thing. I think LLM-based tools are here to stay, but we're the ones who are responsible for how they get deployed. And I think judgment is part of that, as I said, and also putting all of our software engineering on better foundations is really important. And remember, that's a win all the way, whether you're in a system where you've chosen not to deploy them or not, because these foundations are also the substrates for all of our regular software engineering. Thanks.